All right. Okay. You want to say anything, Mel? All right. So anyway, Hajime's talk was a great segue into this. The topic is similar. I probably won't be quite as polite bashing Toe. But that being said, so this will be a talk about TCP and ULP offload. It has kind of the same effects as the previous talk. However, the methods are very different, as we'll see. So right up front, this is not TOW. And I'm using a definition of TOW, meaning this is putting TCP into hardware, the TCP state machine. So yes, we can have endless conversation and debate on this. There's a history behind it. So like Hajime said, we talked about Windows. Chimney had it for a long time and they deprecated it. I actually worked on a startup back in the day, Silverback Systems. We did TCP offload. It was a huge amount of fun, learned a lot. But at the end of the day, it was kind of useless. You could not fix it if there were issues in deployment. With security, you were stuck. And all of those points, they were summarized on this one of Linux Foundation websites. All of these points are true. Security updates are hard. Performance can be hit or miss. Support is hard. Diagnostics, it's kind of an endless list. And like I said before, TCP, it's kind of complex. And not only is it kind of complex, it also is continuously evolving. So if you did this, a TCP offload engine in the modern era, I would expect that it has to be fully programmable, which I believe in last year's Netdev, one of the AMD guys mentioned that they had done TCP and P4. That would be promising, actually. Whether or not you could actually replicate all of Linux TCP is a separate question. And that gets us to that other side effect that we talked about before. If I'm going to do an offload of a kernel functionality, the kernel will only trust that offload if it's exactly identical to its behavior. So the problem is if I have a kernel TCP stack and I have an offload TCP stack and there's behavioral differences between them, then how do you debug the differences? So one connection has this behavior on the wire, another connection has this one. That's a nightmare for somebody trying to debug in deployment. And TCP is an extreme case of that, but we'll see and have seen that even simpler offloads suffer from this problem. So if you're going to offload something and call it a kernel offload, my belief, it has to be 100%. So the system call offload would accomplish that because, in a sense, it's system calls. And for instance, if you really wanted to, you could run a Linux on the SmartNIC, which is actually what we're going to do too. It's just the interfaces are going to be a little bit different. So one of the starting points, so we know that TOW, we've been trying to do it for 20 years, or at least there's a 20, 25-year history on it. I would view it as pretty much a failure. There are a few remaining use cases of it today. I think some of the RDMA over TCP, NVMe over TCP. There are some use cases, very limited though, in data centers, probably within a rack. So we're not really using all the TCP bells and whistles, maybe not even using congestion control. Retransmissions may not exist. So that was kind of the remaining foothold of it. But today there's actually what I call a new motivation for it. And this is the fact that more and more operators, particularly in cloud, they want to get infrastructure processing off of their server CPUs. And this is a statement of where they're running things, not even necessarily how fast or how performing things are. The reason they want this is because they view these server CPUs as precious commodities. And they want those server CPUs to be running their client's code, not what we call infrastructure code, not doing TCP retransmissions or not doing TLS or what have you. So, and the reason they want that's pretty obvious. It's an economic thing. They want to sell CPU cycles to their clients in a lot of cases. So when I first saw this argument, I thought it was ridiculous because basically, if nothing else, even if you have another CPU, say in the SmartNIC, and you're moving the load from one CPU to another without a performance improvement, all you're literally doing is moving the problem. And you're actually, without any other optimizations, you're actually decreasing performance because you now have the overheads of communication between them. But that being said, this argument still applies. I saw this first at Google. So in addition to that, and when we look back at TOE, it's not just TCP that we're interested in anymore. Like we talked about yesterday in the HOMA presentation, applications, they want to work on messages. Messages in TCP or messages over QUIC. So fundamentally, they don't want to spend time reconstructing TCP streams. That would be considered infrastructure. So it'd be really nice if we could just give the application the actual data it's interested in. So an RPC application, regardless of what the transport is, what the RPC application really wants are the RPC messages. So that is a motivation. If we can offload some of the ULP processing and give the application exactly what it processes it, then again, we're offloading the infrastructure. And again, that's even before we talk about performance. Now, that being said, yeah, sure, network speeds are increasing. We do need to improve performance. All of that is completely true. The other aspect of this is also power management. So we've already seen some interesting cases where people are offloading maybe parts of TCP onto a lower power CPU. And one thing that comes to mind, I think there was a Qualcomm part that was offloading just enough eBPF such that when a TCP keep alive came in from the wireless network, instead of waking up the mobile phone CPU, which is expensive power, they used this little tiny chip. It just did eBPF, probably really bad performance, but it was just enough to send the keep alive ACK. And the result of that is they didn't have to wake up the CPU, so they viewed that as a big win. Obviously, on a smartphone, power is everything. And if you can save a few power cycles here and there, longer battery life, so customers are really happy. So there's actually multiple use cases of this. But like I said, performance is still there, but I don't think that's necessarily the first motivation for TCP offload. So I'll get into exactly how we are approaching the problem. It's somewhat similar to the kernel offload presentation, but in our case, we are offloading through AFXDP sockets. So AFXDP sockets are going to be the communication between a host CPU, server CPU running Linux, and the CPU in the SmartNIC, which again, presumably would be running Linux. So our offload is fundamentally going to be offloading from server CPU to a SmartNIC CPU. And the mechanism to do that, or the transport we're proposing, is to use our friend's AFXDP. So what does AFXDP give us? Well, it gives us the ability to create shared queues, which look just like network queues, in the SmartNIC device. And these network queues, they're actually processed by the server CPU and the app CPU. So on either side, what we envision is there's AFXDP sockets, and these sockets somehow map basically to the shared queue pair, one for receive, one for transmit. And on both sides, we can send and receive basically messages over these AFXDP sockets. And these really are messages. I'll get into the format in a little bit, but it's a messaging-based system where we happen to be using NIC queues to do this kind of internal messaging between the host and the SmartNIC. So the cool thing about this messaging format, since these are NIC queues, we decided that we'll just format these as a type of Ethernet frame. So it's really convenient. So Ethernet frames will have a source address, MAC address. We use an experimental Ether type. And that basically does describe a valid Ethernet frame. And it has an interesting property. Someday we could actually offload this whole thing to a different device in the network, since it is Ethernet. But the Ethernet framing really is only, and for our purposes, useful to just make sure if somebody tries to interpret this as an actual packet, it won't go anywhere because it's an experimental Ethernet type. So it's compatible as something we're putting on a network interface queue. So the message body is the interesting part. This is our discretion. So to simplify it, we have just two fixed fields. One is a type, so all the messages will have a type. And these messages will convey the various offload operations we'll get into. It's not going to be a one-to-one mapping with socket calls. It's going to be a little bit of a roll-up, so that's going to be a little bit of a difference. And sequence number we'll use for validating that the messages are being received in the proper order. So the application side, the way it interfaces with this, we have a concept of XTS sockets, XTP transport sockets. The idea here is these are a user space socket library. It has all the normal looking socket calls, so it has XTS send, XTS receive, what have you. The application basically uses this interface. So instead of using plain socket calls, if it wants to offload, it could use the XTS sockets with the same effect, except the connection will be offloaded into the SmartNIC. So the way it flows is the application makes these XTS socket calls. These are mapped to messages. The messages are pretty high level. One message is like create connection. One message is send data, along those lines. And on the peer, which is the smart app CPU on the SmartNIC, we run an offload proxy. So it's pretty much a straightforward proxy. On one side, it listens to messages on these AFXTP sockets. And on the other side, it just manages TCP sockets. So when a new connection request comes in, it gets the message, and it just connects to whatever the addresses are in the messages. So, and then it establishes what pretty much looks like a normal proxy. Once the connection is established, the application can call send. The data goes through AFXDP, through the shared queues, pops up in the SmartNIC proxy. SmartNIC can then just do normal proxy, so it'll just receive data on one socket and send it on another. So again, all of this so far, it's just a pretty straightforward application and a type of proxy, not a transparent proxy. You could make it transparent. We could do the LD preload trick and somehow make socket calls and send calls, the normal ones, look like XTS sockets in an LD preload library. But that's not really the focus. I think that's, in a sense, secondary. So to give an example of these operations, so on the left side, we have the application. It would call first an XTS socket, so we do get a type of socket handle, and XTS connect. When we do the connect, at that point, we actually start sending messages. So the first message is this connect command. The connect command contains all the parameters for the connection, the port, the protocol, what have you. Maybe TCP, it could be some other things. It can also contain some other parameters for ULP offloads that we'll talk about in a little bit. But once that gets into the SmartNIC proxy, sees that we have to open up a new connection. It just does a socket, does a connect. Once it's connected, it sends back an acknowledgement to the peer host. So now the peer host can proceed beyond the connect. And at that point, we start data operations. So on the proxy side, we will just do a receive, so we'll always be ready to receive data. And whenever we do receive data, we actually proactively send that up to the SmartNIC or to the host. So basically, we send a trigger to the host saying there's data ready, put it in host application visible buffers. So at some point on the application side, when it calls XTS receive, the data is there and it returns immediately. So it's a little bit different than the socket offload. So in the socket offload, it seemed like we would call receive, message would be sent to the device, the receive would be processed, and then a message would come back with the data and the acknowledgement. So in that sense, it's one less message to do a receive. At send will have kind of the same property. So in the send case, the application side does a send, XTS send. We create the message, send it down. The message includes all the parameters to send the data. Proxy gets the message, converts that into the proper send calls on the TCP socket. In this case, we don't really need to send an acknowledgement. The sender, once XTS send, put the data into the XTS socket, that's sufficient to say the data was sent, so it'll return immediately. So there's no acknowledgement on the send side. The listener side works kind of the same way. So we create a listener socket using the normal socket bind listen. The XTS variants, we do the command. That command contains all of the information about how to listen, including the ports. And when we get that, we do the whole thing. We do create the socket, bind to the port, call a listen, and then go immediately into an accept. And once we have that, we do send an ACK. The ACK is also needed because we do need each side to understand or to have a handle of its peer. So each side has to know what its peer's handle is for a connection or a listener. So that will convey that. But once we do that, we can get past the listen, and now we can call accept. So both sides running accept. When a new connection comes in, we send a message to the host. And the host does respond with a new connection ACK, again, in order to synchronize the handles. And after that point, we're back into normal data mode, which looks just like on the left, so we can receive data and send data. So close operations would have a similar flow. Either side could potentially, well, the application technically can only close it, so that would result in the message. And the listener, when the connection is closed, it would send up, it could send an acknowledgement or a message, or like a data reply or data receive message with 0 data saying the connection was closed. So that's kind of fundamentally how it works. There's one fairly hard requirement here for the hardware, and that's that the shared queues must be lossless and have in-order delivery. And I didn't think this would be a problem. However, in some of our discussions, there are people who want to put everything through a virtual switch in the device, and that could be lossless. The problem is, if there's any possibility of lossless, then we have to introduce the whole concept of retransmissions and acknowledgements for messages. It would just quickly undermine the whole value of this. Let's wait. I think I only have a couple more slides, so I'm going to try to get through this quickly. That being said, we do need flow control, but the flow control is kind of at the sockets level. That's fairly simple. It's just a credits mechanism to make sure that we're not overflowing sockets. So this is described in some detail in the paper. I'm not going to go into it too much. As I mentioned, the message is to use the experimental ether type. Security is obviously super critical here. The one advantage we do have is that security first can be derived from the AFXDP sockets layer security. Obviously, there's quite a bit of additional work we need to do on top of that. But from a kernel point of view, the AFXDP sockets presumably will be the basis for security, similar to how any sort of other access, like DPDK, would access those queues. Polling is obviously essential. This is actually one question I would have with the kernel offload, how polling is taken care of. So the tricky part about polling, of course, is when we poll, sometimes we want to poll sockets that are offloaded, but we might also poll sockets that aren't offloaded, and we might actually poll things that aren't even sockets at all. We might poll other sort of file descriptors. So polling is incredibly powerful. It also makes it tricky whenever we're dealing with any scenario where we're trying to introduce something else that looks like sockets but isn't, and that's always fun. So there's some there's an explanation of this in the paper, how we deal with polling. It does involve kind of a two layers of polling. First, we poll on the AFXDP socket, and then a secondary poll is kind of on the XTS sockets that we map into that. So I think it's a fairly elegant solution. We haven't actually implemented that. It's kind of on the list to do. One of the critical things here, though, is no kernel changes. This is another thing that people are very sensitive to, especially on the server CPU. We cannot change that kernel easily. And even if we did, it's 2 years to get a patch into a distro, and then some number of years. So the thing I really like about this solution, especially about AFXDP sockets, it has near universal support. So that's good, but primarily no changes on the server side. Now, the app CPU side, I believe we should have a little more flexibility there. The app CPU is a constrained environment, which is really nice. And hopefully the vendors can be a little more proactive in updating the CPUs. And obviously it's a kind of a domain-specific environment, so the kernel can actually be tuned for that environment. So there might be a little bit more leeway on the application side, application CPU side, but we're not going to count on it. So fundamentally, without any other sort of optimizations, other than that hardware requirement of lossless, I believe this is applicable without changing the kernel. Obviously, everybody also wants no application changes. We kind of had that discussion. LD preload's the solution there, but yeah, any solution like this with LD preload has its pluses and minuses. LD preload's been around forever. We've had open onload forever. It hasn't yet taken over the world, so I think it has a place, but that is future work. We also, of course, want zero copy, header data split, message steering. Some of this is actually facilitated by the fact that we're running a separate stack in the NIC, so we'll have a lot more flexibility on things like header data split. So for instance, we can actually do header data split in user space, which gives us a lot more flexibility. So there's a lot of value there. And the other thing is, one of the nice properties of this, and this is true for the kernel offload, once we do the offload, we're actually closer to the hardware, which does give us the opportunities to use some of the hardware offloads a lot easier. So now I have a limited kernel set that can probably be updated. So it's going to be a lot easier to update those kernels and support the hardware offload. So there are advantages to that, which makes me think it's a good avenue to getting these hardware offloads, again, without having to change the host kernel or without having to support these fancy or these fancy hardware accelerations in the host kernel. So I'll mention ULP offload kind of briefly. So like I said, it's not just TCP offload anymore. Applications can benefit if we can give them a full ULP offload. Obviously, this begins with TLS, but we can percolate this up in multiple directions. Some people want compression. Some people want RDMA. Some people want NVMe over TCP. Some people want RPCs of various flavors. Just a whole bunch. And we have actually some fairly good support for this in the kernel in some sense through store parser, but that is always somewhat agnostic to the actual thing that we're offloading. It doesn't actually process the bits of the offload. In the best case, we can kind of do the demarcation and at least deliver full messages to the host. But in this case, since we're running all this in user space, we actually have more opportunity. So somebody wants TLS plus compression plus erasure coding plus all over with RDMA. You can actually build that stack pretty easily. And I do like the term stack here. It kind of reminds me of streams going back to my old Solaris days. But if we can think of this connection or this socket that the user application gets, it can now think of it as an HTTP2 socket or an RPC socket without worrying about how, when I send a message on this socket or receive it, how the message actually got onto the wire. So generally, it's kind of an interesting property. So we can have these ULP sockets. This is an example of a HTTPS socket. So we have implemented this. Unfortunately, we didn't fully finish the performance analysis. I think a lot of the performance analysis would kind of be similar to what we just saw, so I'm not going to go too much into detail. But the performance measured here actually would be utilization on the host CPU, which again is the first target, is to reduce the CPU utilization to an infrastructure. The performance differences would come from the fact that we're no longer doing the TCP processing. We're no longer doing IP processing, Ethernet header processing. All of that kind of goes away. We do have a sockets interface, but it's AFXDP sockets, which hopefully is more efficient than going through the normal kernel sockets and system calls. So there's a lot of advantages to that. And obviously, when we combine this with something like TLS, we would fully expect that all of the cycles going into TLS, they would no longer appear on the host side CPU. But again, if we're just moving that, and if you went to the NIC CPU, you'd obviously see these cycles appearing there, which would motivate TLS offload. But then again, it's a simpler problem because now we're offloading from a constrained OS to do TLS offload. So implementation status, we did bring this up on Bluefield, and looks pretty good. So the plan is we'd like to get this, have an open source, at least a draft version of this sometime in Q1 of 2024. All of this is basically put into a library, at least on the application side. So we have something called the XDP transport library. That's for applications. That'll provide all the XDS socket calls. And we have the user space proxy running in the SmartNICs. In future work, like I said, we need the in-depth performance analysis, the advanced features, the offloads, LD preload. Hopefully we have enough work other people have done. I'm hoping that's not terribly difficult, so hopefully we can adapt something like open onload. But then the various ELPs, this is a little more interesting. So I think we intend to do a fair amount of work on where to go with that and how to support it. So anyway, so in summary, I'll just go back to my 80-point font slide. Not TOW, but TCP offload. Not designed for performance, but designed for this modern idea. We're just trying to get CPU cycles and infrastructure out of these expensive host CPUs. Hopefully get them into some other CPUs, and obviously, and then we have the questions of whether those other CPUs can keep up with it. It's a separate story, but that's a model that this is kind of espousing. Thank you.
Excellent, Tom. Thanks. So before we ask for questions, there's a skeptic online, and this is what he says. He says he doesn't believe his grandmother knew anything about TCP. Right? To the title of your okay, anybody with questions? Yep.
Oh, there we go. Tom, thank you for your talk. Having not done TOE, but having talked to TOE people who did the LD preload, the hard part about LD preload is all the things where you have things like socket semantics where they run a web server and they fork another thing and the other thing has the LD preload and has to inherit the state that was in the other process and all those kind of corner cases. You know, for the simple case of iPerf with LD preload, it's easy. But for real world applications, and then the other corner is cases, you know, the thing crashes and making sure you recover.
Yeah, that was kind of a fundamental problem of TOE. I mean, corner cases are the bane of an acceleration. And it can be so bad. You know, I look at something like TLS offload, and the corner case there is packets are received out of order. And now I have to do this whole orchestration with the host. The problem with any of these sort of offloads, the opportunistic ones at least, which is almost all of the ones I can think of, the problem is if these corner cases become the common thing. So if they're not just, if your slow path isn't really rare, you fall into all these corner cases. And what we found is having an acceleration, and I won't claim that this is immune to that problem yet. I think there's some mitigations. What we found is almost for any acceleration, other than maybe checksum offload, if you fall into the wrong corner case, you may actually arrive at a point where the performance of your system is worse than you had not even had the acceleration. So this is super, super difficult problem.
But Tom, I think what he's talking about is a slightly different tangent, which is using LD preload specifically. By the way, I implemented the alternative open onload for Precision IO. So the problem he's talking about is you open an FD, you decided that you're going to onload it, and then you do a dupe, or you send it through a different socket and do a read on the far side, or you do a fork, and then you have shit on your hands because you have no idea where this FD went, and you don't know what its offload state is, and you have to go resync it, and it becomes problematic. But that wasn't my question.
It is an information. It is a loss of information.
Yeah, and I think there is a big problem with the LD preload strategy as a result. So I think there is a chance here. And actually, I want to address something that John asked last time as well. I don't agree that hardware is the only way you can move things. I think you have to rearrange. And I think the opportunity here is a thought for Linux to rearrange what a socket interface or intercept looks like. I think there are ways to do dupe. Like actually, that's what we did. We would dupe everything and keep a shadow FD around and keep all the state around, and that's the only way you can reconstruct the state if you want to. But there are ways in which you can do it, and I think there is a chance here between your talk and the previous talk. I think there is a overall statement, because sendfile has the same problem. I have a pointer to a kernel object that used to be valid in some FD's context, and it isn't anymore, and I don't know what it means. The point I wanted to talk about was that why are you sending the payload inline in your AFXDP call? Keep it as a pointer that will allow you to address your reliability concern as well. Because if it is just a pointer to memory that the user is going to manage anyway, pull it out of band, and then you are reliable across your transaction.
Which part out of band?
So your current method, it looks like a real socket, right? Which means you're going to do a copy. Every time I push, I'm going to make a copy into the socket.
Well, you mean of the data?
Of the data, of the payload.
Okay, so that I glossed over the details, but you're right. The interface could be coupled such that we can pass pointers. We can use all the fancy CXL. The critical part here is, and this is another thing about NICs, it technically is a closed system. The NIC is part of the host. Now, we haven't been able to exploit this very well in some sense. I call this extending. Sometimes we want to extend the stack into the device itself. One way to do that, yeah, if we can pass pointers, so yes, fundamentally copying data bad. We want zero copy, we want to do that. I don't see any reason why this interface would preclude that.
So I think I agree also with this problem of LD preload, but also it's a problem because you are asking VM owners to put something that they need to be aware of, and worse of it, they need to update when you fix whatever you have in this interface. Also, I think there's another problem with the kernel that you are going to use in the device. How are you going to be sure that whatever is the user running is compatible with the kernel that you have there?
Well, for that, the requirements need to support AFXDP, XDP, AFXDP, and other than that, the kernel requirements, assuming we can get the queues, but the queues are the hardware thing. So like I said, the one hard requirement we have here is we need this concept of shared queues, where host can read and write them, app CPU can read and write them. They're not network queues. They don't go out to the network. They're internal queues. If we establish that, even if that's going through some sort of switch or whatever, but if we establish that path and it's lossless, that's the hardware requirements. Software requirements, I don't know of any other than the AFXDP and XDP support that we already have.
Yeah, but you are, maybe I'm understand this wrongly, but you are telling the clients, use these system calls. The system calls
speed this up, please.
Are going to have some kind of functionality that they expect. And if you don't update the kernel to the newer one that they are using or whatever, you have probably a problem there. This kind of compatibility is where I think is.
Okay, it sounds like we need a breakout session, guys. We're going to stop it here. Thank you, everybody. Let's give a hand to Tom. Thank you.